This is the fifth section of the forces and motions chapter, and this looks at connected particles. Now, this is often a topic that students find tricky and difficult to understand, but there are just a couple of rules really you need to remember. The first thing is, if you've got particles traveling connected together by a string or rope or something like that, or a bar of some sort, and they're moving in the same direction, then if you just work out the total mass and the total forces, you can work out the acceleration. So for example, let's say I've got two masses here, mass 1 connected to mass 2 like this, and let's say there's a pulling force here of P, and there's a resistive force on M2, mass number 2 of force 2, and there's a resistive force here on mass 1 of F1, and it's accelerating in that direction to the right. Okay, so we've got these two masses connected by some string or rope in between. So what we will do is we'll put the tension on there. And it's just worth reminding you that tension pulls from the object it's connected to, and thrust pushes. So thrust would push into the object. So if I've got something like this, tension would go like this, pulling away from it, whereas thrust would push into the object. Right, so let's go back to my diagram here. So these two masses are connected by some string. There's tension pulling away from both of them, okay, and we want to find the acceleration. Since they're going in the same direction, if we find the resultant force by looking at all the forces, that will equal to the total mass times acceleration. So in a diagram like that, if I wanted to find the acceleration, the resultant force is going to be P minus F1 and F2. Now I don't need to add these. I'll be adding T and subtracting T, wouldn't I, because of the direction they're going in. So maybe I'll put like a thing here to show that this direction represents positive forces. The resultant force is just going to be P, the pulling force, minus the two resistive forces. As I said, I could actually put in plus T minus T, but that makes no difference, yeah? They will cancel out. So it's just the total pulling force, which is P, minus the resistive forces F1 and F2, and that will equal the total mass, so M1 plus M2, times by the acceleration A. Since they're moving in the same direction, we can just clump together, and that's my wording, clump together the forces and masses to find the acceleration. Just clump it all together as one. They're moving in the same direction. However, if I wanted to find the tension here between them, I then split them up. Okay, so to find the forces between masses, and that might be tension, thrust, or simply the force that one mass exerts on another, then we split them up. So if I was to look at this, I have two choices. I could take mass 1 and just look at the forces on mass 1, which would be that frictional force the tension that way, and I can use the acceleration to work out T. Or I could look at mass number 2, and the forces on that are that pulling force there, the tension here, and again I know the acceleration, so I could use that to work out T. So basically it's like you split it up, either look at the forces on that individually or that individually to find this force in between them, but to work out the acceleration, just clump it all together and work it out that way. Right, so we have two particles P and Q of masses 5 and 3 kg, which are connected by light inextensible string. They're being pulled. So let's do a diagram like this. So we've got mass P, we've got mass Q. One is 5 kg, the other one is 3 kg. They're connected by light inextensible string. So there is a tension there and there when we need to split it up. And P is pulled by a horizontal force of 40 newtons. So let's go that way. Along a rough horizontal plane. Okay, let's make this rough then. Particle P has a frictional force of 10 newtons. So let's put that in there, 10 newtons. And Q has a frictional force of 6 newtons. There we go. There's my diagram. It's going to be accelerating in that direction, the direction of the pulling force. And part A says find the acceleration of the particles. So we just clump them together. Okay, so using F equals ma, Newton's second law, what are the total forces? Now I'm going to take this way as positive, my positive force. Now what's the pulling force? 40. Okay, I need to subtract any forces going the other way. Well, they're the two resistive forces, so take away 10, take away 6. That is the resultant force of the whole system, the whole thing together, equals, now for mass we use the total mass, so 5 plus 3 times by the acceleration, which we need to find. So this is a easy enough equation to solve. So 10 minus, so 40 minus 10, which is 30, minus 6 is 24. So that's the resultant force of the whole thing, equals 8A. So from that, divide by 8, and we have not 8 equals, but A equals 3 meters per second squared. So there we go. That's the acceleration. So notice how we just clumped everything together. The total mass of the whole thing, the total resistive forces, and the total pulling force. Part B, we want to find the tension in the string. This is where we need to split it up. Now I'm going to show you the two ways we can do this. So if I look at the forces on P, so forces on P, so I'm going to do it this way or this way. You can choose either way. Look at the forces on Q. Whichever way I do it, I'll get the same answer. So you choose one or the other. So let's start with P. Let's try it this way. Right, what are the forces on P? Well, there's a pulling force of 40 newtons. There is a resistive force of 10 newtons. And there's this tension force here, which we need to find. If we were using Q instead, we would have a mass of 3. We would have a resistive force of 6 newtons here. And the only other force actually directly attached to Q is this tension here. Right, so let's look at if we were looking at the forces on P to solve this. Right, we know that it's accelerating in this direction, or both of them accelerating in the same direction. So that tells us what's positive and what's negative. So the resultant force on P is going to be 40 minus 10 minus t, because they're both going the opposite way to the direction of motion, equals ma. So 5 times by a, and we worked out a, that was 3. So we have 30 minus t equals 15. So t is going to equal 30 minus 15. So you get t equal to 15 newtons. Now that would be fine, we can stop there. Now, what if I looked at the forces on Q? Do I get the same answer? I should do. It's just my equation is going to look slightly different. So if I look at the forces on Q, again, it's moving to the left. So the resultant force is going to be T minus 6. T's pulling, 6 is going the other way, so it's a negative, equals ma. So this time the mass is 3. A, the acceleration is still 3. So I have T minus 6 equals 9, add 6 to both sides, and I will get T equals 15, the same answer. So in this particular question, you could look at the forces on P or Q. In some questions you don't have a choice, but here we did. And whichever one we choose, we'll get the same answer. Part C. Explain how the modular assumptions that the string is light and extensible have been used. Okay, well, light just means that we ignore the string's mass. So I'll just put ignore mass, or ignore mass of string, of the string. Inextensible basically means that the string between them doesn't stretch, so they're both moving at the same speed, which means they have the same acceleration. So same acceleration, and you could go on to say that it's because the string is not stretching. That meant that actually we used 3 in both, didn't we? We used the same acceleration of 3. That was the assumption that we made, and we did not include the mass of the string in our working, so that's the light part of the assumption that we make. Okay, so we've got a light steel pan attached to a vertical light inextensible string, so there's going to be tension there, so let's just put a T there. Scale pan carries 2 masses A and B, so there they are. One is 400 grams, one is 600 grams, so we've got a total weight of 1 kilogram. The mass of A is on top of B as shown in the diagram. The scale pan is raised vertically using the string with acceleration 0.5 meters per second squared. So let's put the acceleration there of 0.5. Part A says find the tension in the string. Now in part A, the tension in the string is not a force between the masses, it's a force outside the masses. So I could think of part A like this. I want to find the tension here. I'm going to have the combined, the total weight here. It's accelerating in this direction, and I want to find T. Now I can do that because if I put both of the masses together, the 400 grams and 600 grams, I will get 1 kilogram. So the weight of this is going to be 1, the mass times the acceleration due to gravity, which is 9.8. And I know the acceleration is 0.5. So the resultant force is going to be T minus W equals M, so the total mass, times by A. W is 9.8. So T is going to be equal 0.5 plus 9.8, which will be 10.3 newtons. That's the 3 significant figures. I could also give the answer to 2 significant figures. So notice in this part of the question, what we're able to do is just to clump the masses together, treat it as one mass because they're both going in the same direction, and we're looking at a force that is outside of the 2 masses. Now in part B, I want to find the force exerted on mass B by mass A. So if I put out a diagram, I sort of want to find out what's this force. What force is A exerting on B? Now that's going to be quite tricky to work out. And the reason why it's difficult to work out is because there are multiple forces acting on B. And that's difficult to work out. However, there are only two forces acting on mass A. If I was to draw a diagram for mass A, there are only two forces acting on mass A, the 0.4 kg, and that's its own weight going down, which is going to be 0.4 g, and a force pushing up, which we'll call R. It's like the normal reaction, but it's more than a normal reaction because that normal reaction is causing A to move up. So on A, there are only two forces, where there are multiple forces on B. It makes it a bit too complicated to work out. Now, why can we use A instead of B? Well, as we've shown here, this is the force that we want to work out, but actually that's equal and opposite to this force. I could draw it at the top or the bottom of A, and that is the force exerted on mass A by mass B. And we can use Newton's third law to say that those two are equal. So I'll write this down. By Newton's third law, and I'll write it like this: the force exerted on mass B by mass A, which is what we want to work out, is equal to, was equal and opposite to the force exerted on mass A by mass B. And that's what we're going to work out. We're going to work out the force exerted on mass A by mass B, and that's this, the thing that we've labelled R. This is the force that B is exerting on A, which is equal to the force exerted on B by A. But this is complicated to work out because there are multiple forces on B, and we'd need to work out what those forces are. But on A, there's only two forces, the normal reaction going up and the weight of A going down. So the resultant force in this case is only just going to be R minus 0.4 G, that's from our diagram, equals MA, 0.4 A times by 0.5, that's the acceleration. So R equals 0.4 times by 0.5, which is 0.2, plus 0.4 G. And from that, we will get R equal to, let's work this out on our calculator. So 0.2 plus 0.4 times 9.8, and we get 4.12 newtons. Okay, and we can leave it like that. That's three significant figures, or we can change it to 4.1. So sometimes it's easier to use Newton's third law to say, okay, let me work out the equal and opposite force. And in this case, it was easier to work out the force that B exerts on A, which is this, than the other way around, because then we only need to look at mass A, the one at the top, because there's only two forces, one pushing up, one pushing down. But on mass B, you've got the weight of A pushing down, you've got the normal reaction of B pushing up into A, you've got the normal reaction of the bottom of this steel band pushing up into B. it's too complicated to work out that way. So we use Newton's third law to find the equal and opposite force. Okay, part C, we want to work out the force exerted on mass B by the steel pan. Now actually, that force is actually an outside force. It's not an inside force. So there's our tension here. We want to work out what this is. Let me call that S. This is the force, so we don't need to swap this one around. This is the force that the steel pan is exerting on mass B. This is pushing up into mass B. So basically we just want to work out what's this. Now you can see from the diagram actually, without doing any working, because this steel pan is light and we're ignoring its mass, can you see the tension gets transferred straight to S, and that is the actual force exerted on mass B by the steel pan, this S, pushing up into B. So I can see actually that T equals S, and S, well, T was 10.3, so S is 10.3. So actually, without doing any working, I can see that that force pushing up into the 0.6 is equal to the tension. Now, if we actually wanted to do some working, we could say, well, because I'm considering a force that is outside of the two masses, I can clump the masses together to get 1 kg and say, okay, this is the force that's pushing up into B. And then what have I got down here? Well, I've got the total weight, which is 1g. So if we're going to do some working, we could also say that S minus G equals MA. So that'll be 0.5 times by 1. So S is going to be 0.5 plus 9.8, and we still get 10.3. So this is a part of the question where we can clump together the masses as well, because S is like a force that's acting outside of the two masses, not between them. Now I know these types of questions can be quite confusing for students. So if you're looking at the force that's exerted by one mass on another and it looks difficult to work out, then use Newton's third law and just swap it around. And often it's easier to work out. And really what we're trying to get to is some sort of mass where there are only two forces acting on it. That will be easier to work out than a mass that's got all these different multiple forces acting on it. You should now be able to do exercise 10E on pages 171 to 172 of the textbook. So just a quick recap here. So when we've got objects traveling in the same direction, let's say like this, and let's say that they're maybe joined by some string, something like that. Let's say we've got a pulling force here, and we've got some friction or resistance here, and you might have friction from both of those. So let's call this friction 1, friction 2. We'll call this the pulling force, and we've got our masses, mass 1 and mass 2, and we have tension here pulling by each, and let's say that this is accelerating in this direction. Then our resultant force is going to be the pulling force, take away the two frictions, F1 and F2, and that will equal the total mass times by A. So when we're trying to find an outside force, now what I mean by that is a force that's not between the objects, then we can just clump everything together, clump together masses. That's not a technical term. But if we want to find the inside force, so in this case it would be the tension. So inside force, then we need to split them up. Okay, split up masses. So we would consider the two separate things. So we would either look at mass 1 and the tension and friction, or we'd look at mass 2 and we'd have the tension going this way and the pulling force going that way, and also the friction, but this will all be accelerating in this direction anyway, so we can still use F equals ma. And if you're doing a question and it's difficult to work out, let's say the force exerted on A, or mass A by B, then you can use Newton's third law to swap these around. Okay, so Newton's third law will allow you to say, okay, let's swap that around. Is it easier to find the force exerted on B by A?